Hello, I am Ahmed Abdu from the Technical University of Munich. Today I will present gaze-enhanced cross-modal embeddings for emotion recognition. This is joint work with Ikta Sood, Philip Muller, and Andreas Puring. Emotion expressions are multimodal by its nature. Emotions can be expressed through several channels such as facial expressions, audio, gaze signals, body movements, body temperatures, and other signals. However, emotion recognition is often limited to one of these modalities. As in a phone call, you have access to only the audio signals to the person you are talking to, but you are still able to do the recognition task. Emotional recognition in the context of machine learning is predicting the expressed emotion by training a machine learning model using certain features. One way is monomodal learning, where a source of input or a modality is given to the model during a training time, and the same modality is used at testing time. For example, a model that uses audio signals during both training and testing to perform audio-based emotion recognition. Emotion recognition can also be done through multimodal learning, which is training the model by more than one modality and using the same modalities at testing time. For example, a model that uses facial expressions, audio signals, and gaze signal both at training time would also require that all modalities appear at testing time. Multimodal learning often shows better performance at the tasks which are multimodal by its nature, as in our example today, emotion recognition. More recently, cross-modal learning has been introduced for the emotion recognition task. In cross-modal learning framework, a model that can learn a task from different input modalities but requiring only one modality at this time. In the phone call example, a cross-modal learning framework would be a model that uses multiple modalities during training time to enhance its performance at audio-based emotion recognition. Gaze in emotion recognition. Eye gaze behavior has been studied widely in psychology of emotion expression and perception, and has been shown that gaze can reveal information about the user's attention and intentions. Also, specific eye movement behaviors, as gaze direction, coupled with facial movements, are relevant when expressing and perceiving specific kinds of emotion classes. And the use of the perceived gaze direction has been shown to better assist the humans to distinguish between emotion classes. Despite all of these works, to the best of our knowledge, no emotion recognition approach incorporating gaze with both facial expressions and speech has been proposed. From these points, we introduce our contributions in this work as follows. First, incorporating an explicit representation of gaze in the said cross-modal emotion recognition framework. This proposed framework improved over the previous state of the art for video-only and audio-only emotion recognition. Finally, evaluation experiments for which gaze feature set to use and how specifically to integrate these gaze features in our cross-learning framework. Here is our cross-modal embedding framework summarized in this figure. We start by extracting audio features and passing them through an audio encoder to get the audio embeddings. Simultaneously, we extract the features and the gaze features and pass them to the gaze-enhanced visual encoder to get the gaze-enhanced visual embeddings. These two kind of embeddings, audio and gaze enhance, are living in the same space, and we call that the embedding space. And for how we get the gaze-enhanced visual embeddings, we propose a novel gaze-enhanced visual stream network. This network incorporates a dedicated gaze representation into the visual stream, mapping both the visual and gaze features to the same embedding space. The integration of these two input modalities can be done in two ways. First, after processing each feature stream with its corresponding encoder, we concatenate both embeddings to form a double-sized one, then projecting them to the embedding space with a projection layer, and we call that a model-level fusion strategy. Second, we concatenate the raw features before being passed to a single encoder that processes and projects them to the embedding space, and we call that an early fusion strategy. The next part is the triplet training, which allows the embeddings that belong to the same emotion class to be similar to each other in the embedding space regardless of their input source, and also allows the embeddings to be dissimilar if they belong to different classes. While the triplet loss imposes these said constraints on the embedding space, these embeddings are used to train the shared classifier in joint fashion. This classifier takes an embedding from the embedding space and maps it to one of the emotion classes. This classifier is agnostic to the modality of the embedding, which allows the classifier to use both the audio and visual embedding alternatively while training. These said points, audio and gaze-enhanced visual streams, triplet training, joint training, summarizes our cross-modal learning framework. For the features used in this framework, for the visual features, we first applied the open face tool over each utterance to do the face detection and alignment per frame. And giving these detected faces to the VGG phase network, and we extract the features of the FC7 layer. OpenFace is an open source toolkit that do facial landmarks detection, facial action units, and eye gaze estimations and other tasks. While for the audio features, we use the OpenSmile toolkit that extracts the EG Maps feature set for each video. While for the gaze features, we use the OpenFace output, especially the gaze estimation output, as base feature. Then we calculated statistical features upon these base features as maximum, minimum, average, and others. And a detailed list of the base and the calculated features of the gaze feature set is in the appendix. We use the calculated statistical gaze features in two ways. First, we extract the features on window of 1 second, resulting in as many feature values per window as there are frames per second in the input video. These window-based features can be used both in the early as well as the model-level fusion, as they can be aligned with the frame-wise facial features. Second, the model-level fusion scenario, we investigated a version of the gaze features where we average the features that were first computed on the window level across the whole video. In this work, we used the 1-minute gradual emotion or the OMG behavior dataset. The dataset consists of 567 monologue videos collected from YouTube with an average video length of 1 minute. The dataset is suitable for emotion classification tasks as each utterance is labeled with one of the 7 labels: neutral, happy, sad, anger, disgust, fear, and surprise. And this is the class distribution for the number of the samples from each class. As we can see, there is high numbers for neutral and happy, and a very low numbers for fear and surprise, which reflects the distribution of the emotion that we express and perceive on our daily life. This is random sample of one frame for each gaze direction from the dataset. From the set of the frames where the phase detection and the gaze estimation was done with high confidence by open face. And for the results, this table shows the F1 scores for the different experiments. The best video-only method was averaging the gaze features and using model level fusion, and it was 45.0, while the best audio only is windowing the gaze features using early fusion, and this is 43.4 F1 score, both improving over the previous state of the art and also over no gaze experiments. And to gain a deeper insight into the performance of our gaze integration method, we conducted a performance analysis per emotion class. And we are the first to give this class level performance for OMG dataset on the classification task. We compared the performance of our gaze-enhanced cross-modal triplet training approaches to the corresponding no-gaze appellations. For video testing, we observe the improvement for our gaze-enhanced method for neutral, happy, and sad. On the other hand, we obtained lower F1 score for anger and disgust. The improvements are aligned with the number of the training samples available for each class. Our gaze-enhanced approach improves for the classes with high numbers of training samples and has a disadvantage on classes with lower number for training samples. Similarly, for audio testing, our gaze-enhanced approach improves the classes neutral, sad, and anger, and is on par with no gaze baseline for happy. We again observe zero performance for fear and surprise, and this case for audio also discussed. Our gaze-enhanced visual streams utilizes a set of gaze features proposed for emotion recognition by Oldwire et al. Meanwhile, a different set of features was proposed by Van et al., which, to the best of our knowledge, was the only other feature set proposed in the emotion recognition literature that utilizes the gaze estimates from RGB video via OpenFace Toolkit. In both audio and video testing scenarios, the best performance is achieved using the feature set based on Oldwire, while for the video-only testing, the features of Oldwire are always superior to those of Van et al. The results for audio-only testing are more mixed. We visualize the distribution of gaze estimation for each emotion class by projecting them on the camera plane, and we plotted the kernel density estimation of these projections. The most noticeable that the gaze distribution over sadness is very concentrated, which is in line with the passivity that is associated with this emotion. On the other hand, surprise is more spread out. For the limitations of this study, a key prerequisite for every gaze integration method are the available gaze estimates provided. And we use the gaze estimates by OpenFace, which potentially missed subtle gaze cues that are not well represented in the gaze estimates. More accurate gaze estimates obtained from dedicated eye tracking system should be examined in future work. This poses several additional challenges. For example, gaze estimates might not always be available due to occlusions and extreme movements, as in this case, these are random samples from the set of frames where OpenFace was not able to detect the faces and perform gaze estimation with high confidence. For the applications for this study, we see our method that can be applied to in any HCI scenario where an RGB video of adequate quality to perform gaze estimation is available. So in case we want to do audio only emotion recognition, gaze-enhanced cross-modal emotion embeddings are promising in this application, especially when unstable network connections results in a low quality or dropped video, so we rely on the audio at testing. On the other hand, in an educational setting, emotion recognition can be valuable to access students' evaluation or learning material, as students are often silent during learning or maybe in a location with high ambient noise, so we rely on a video-only emotion recognition. Conclusion: we integrated gaze into a cross-modal training framework that allows single-modality emotion recognition at testing time. We used and proposed enhanced visual stream network through gaze integration. This framework outperformed the previous state of the art for video-only and audio-only emotion classification. And our visual stream network leads to clear improvements over baselines without gaze integration. Thank you.